Um, Hi guys. Hi guys. Let me just finish admitting people into the meeting. How you guys doing? So before we get started on, hang on, sorry. Before we get started on stuff, I wanted to point out that the lecture video from yesterday's class is up on our Canvas page. I put up there yesterday. I also uploaded it to the YouTube channel so you guys can have another option. The one on the YouTube channel is the actual length of our lecture. The, the video for yesterday's class, apparently the waiting room wasn't set up correctly so that the video started like a half hour before the class actually did. So I think I told you like skip, this first however many minutes, to the actual lecture right there. But hopefully today the lecture will, the video will represent just the lecture and not people waiting. At any rate, you guys should be able to see that. If you guys can't have access to that or can't see that, let me know. I'll see what I can find. But it should also be up on the YouTube channel too. Before we go ahead and get started on finishing up chapter 1.1, right, because I have a couple examples that I want to talk about, some things I want to clarify for chapter 1.1, then we'll move on to chapter 1.2. I want to ask about homework for chapter 1.1. Now, normally when I teach in person, we end up going over some homework problems. We end up going over some homework problems at the beginning of class. To do that, let's see. I'm gonna manage all this stuff here. I have people come up to the board and we go over these homework problems, but it's a little harder to have you guys come up to the board. We're all here on a video, but if anybody has like a question about last night's homework that they want to ask about, the homework is due next Thursday, so you're free to try it over the weekend and then ask again on Monday or Wednesday's class. But if you have any questions that you want to talk about for chapter 1.1 homework, I'm happy to go over them. Anybody have a question they want to ask? If you want, you can put it into the chat. I'll take a look at the chat right now. I have a harder time looking at the chat while I'm actually lecturing because there's too many things to pay attention to. But if you have a question on homework and you don't want to ask it to the class verbally, you can type something into the chat and then I'll take a look at that homework problem. Or not. You guys can think about it and then ask me on Monday. Okay, on Monday probably I'll end up just picking a problem or two and then we can talk about those in class so that you have those. Okay. Are you confused on question 21, homework for finding the final equation? Let me see, what's question 21? Can you bring it out? Let me just see. 21, oh yes, so what's the question? Write an equation of the secant line of the function between the endpoints of the interval. Leave your answers in slope-intercept form and the same variable names in your equation that are used in the given function. So we're given j of z equals z minus 1 times z minus 2. We're going on the interval from 1 to 2. So yes, so somebody asked about the homework this week is due September 17th. That's correct. So the homework is going to be due when we have a quiz, right? And we don't have a quiz this week, right? We're lucky we don't have a quiz today. But we will have a quiz next week, which according to my calendar is the 17th of September. So the homework will be due. I'll collect it. I just posted midnight, as your due date on Thursday for passing in the homework. But remember, you have a quiz. The quiz availability will start on Thursday, and I think we can maybe by noon on Thursday I'll start the quiz availability so that you guys can have a 24-hour window for the quiz. But the homework will be due next Thursday. All right, so this is question 21. So we were asked, we were given y equals j of z equals z minus 1, z minus 2, that's a z. We're going the interval 1 to 2. Okay, so now what we want to do is you can multiply this out if you want to, or you can leave it like this. Either way is fine. I think it might be easier to leave it like this. If you multiply it out, like if I leave it like this, you can see along this interval that I have zeros at this particular. You guys see that? Okay, it looks a little blurry. All right, so what I want to take a look at is delta j over delta z. Okay, is my average rate of change. So I'm going to say j of 2 minus j of 1 all over 2 minus 1. So this is my function, right? And I'm plugging in my endpoints because they said they wanted us to do the average rate of change for these endpoints here, right? So now what I was trying to do is I'm going to go 2 minus 1 times 2 minus 2 minus 1 minus 1 times 1 minus 2 all over 1. Well, look, here's a 0 and here's a 0. So my slope's actually equal to 0, right? So our slope is equal to 0, okay? Which means basically if I have a point on this equation, if I go j of 1, I'm going to get a 0. That's my point. So my point is equal to 1 comma 0, okay? So if I plug that in, my point slope form is going to look like y minus 0 equals 0 times z minus 1, right? It's y of z instead of y and x, so that's why there's a z here instead of an x. So y equals z, y equals 0 times z, essentially, so y equals 0 is the equation of our secant line. I know it seems a little confusing, right? Because it's, and I think they're just trying to trick you. So like, can you work through the whole formula for things and then recognize that the endpoints actually form zeros of our parabola, form zeros of our parabola, right? So the slope, okay, is going to be a 0, right, at that particular point. So our equation is y equals 0. I have a trick. Question 21. Any other question you guys want to talk about? Okay. All right, you guys can think about it and then ask me on Monday. If I don't have any questions on Monday, I'll just pick a problem or two and then I'll talk about it there. Okay, but it'd be great if you guys could actually take a look at it because you don't want this to pile up. All right, so what I want to do today, is finish up chapter 1.1. So I've got, I'm going to do example 4. We have example 5. It's a stepwise function, but what I'm going to do for example 5 is I'm going to work through the solution and I'll put the solution here and I'll scan it in and give it to you online. I'm not going to spend time on it in class because we just had this example 4 and then a couple of like notes that I want to give you guys just to make sure that you have the idea about what's going on with certain things. Okay, so example 4 says we have a spherical balloon. We want to know what's the average rate of change of the radius of the balloon with respect to, this is a typo, with respect to the volume of the air inside the balloon as the volume changes from 20 cubic inches to 30 cubic inches, right? So we've got a sphere, we're blowing it up, we're inflating it, right? And so the radius is going to be changing, right? As you inflate it, the radius changes. So what's the average rate of change as the balloon goes from this volume to this volume? Okay. So the first thing I like to do when I get problems like this is I like to remember my geometry, right? So I've got a sphere, right? We know balloons in real life really aren't spheres unless they are, but most balloons are not spheres. But we reduce them down to spheres because it's easier to do the math on here. So remember about your sphere, right? My cross section is a circle, right? But the radius of a sphere is the radius at the widest point at the equator here. Okay, so that's our radius. So let's see, sphere. And then I have to remember from my geometry days, what's the volume of a sphere? 4/3 pi r cubed, okay, is my volume, because that's what I'm doing here. I'm doing things, but the question says the radius with respect to volume, right? And I'm given volume, and I'm looking at things, how does the radius change? So this is the thing that I'm solving for, right there, okay? So what I want to do is, because we want radius, the function of volume. Helps sometimes to write it out, just to get your brain thinking about it as a function of volume. Okay. So that means I need to take this equation here and then solve for r. So what I'm going to do is I'm going to write volume. I'm going to divide by pi. I multiply by 3/4, right? And that's going to equal to r cubed. And I have to take the cube root of it. I'm going to leave it as a fractional exponent. Okay, it's the same thing, but I'm going to take the cube root of it. So that means my radius as a function of volume, right, is equal to volume over pi times 3/4 raised to the 1/3. Okay. Well, this thing here, 3/4 all over pi, is actually just a constant. Right? 3/4 of pi to the 1/3 is a constant. So what I'm going to do is I'm just going to rewrite it, because sometimes if I'm, you don't have to do this. You can just leave it as it is. But sometimes if I say, if I go 3/4 times 1 over pi, the 1/3 times volume, 1/3, this here is a constant. Okay, so then I can more easily pull it out when I'm actually doing some of the work. This is the radius, the function of volume. Okay, because I have to take the average rate of change, so it helps to pull out the constants, right? So I'm just dealing with plugging in numbers into one spot. You don't have to do that. You can, leave it as it is. All right, so now our average rate of change that we're looking at is our delta radius as a function of volume all over delta volume. Okay. So let's write that out. So I'm going to go my radius as a function of when the volume is equal to 30 cubic inches minus my radius as a function of when the volume is equal to 20 all over change in volume, 30 minus 20. Okay. So let's do this out, and then this is going to be, I'm going to factor out this constant term, right? So I'm going to say 3/4 all over pi to the 1/3 times 30 to the 1/3 minus 20 to the 1/3 all over 30 minus 20. Okay, so all I did was factor out that constant term. You don't have to do that if you don't want to. You can leave it in here. Just make sure you don't forget it when you're actually calculating things out. Okay, so this, once I work through all the math, watch your order of operations on everything. Once I work through all the math is 0.02436683. We go far out in our decimal places just to show you. Watch our units, inches per cubic inches. Okay, this says our radius is changing as a function of volume. Do not simplify this. This isn't something to simplify. This represents a rate. Okay, our radius is represented in inches. Our volume is represented in cubic inches. Okay, this is radius per volume. Okay, so this is our answer. I'm going to write it in words. You don't have to write it in words when you go to answer things, but I'm going to write it in words so that you can know what it is that we're talking about here. So this means our radius length grows by 0.02436683 inches, with every cubic inch of volume, let's write this down, of volume between 20 cubic inches of volume and 30 cubic inches of volume. This is just for you to know what we're trying to do here. Okay, you don't have to write this down as part of your answer on things. This is your answer right there. Okay, but just so you know, think about it this way. I've got a sphere, it's a balloon, right? I'm blowing up this balloon. When we didn't calculate this out, it'll be interesting to see how this is going to change when our volume changes from, say, 1 cubic inch to 10 cubic inches, because, when you first get a balloon and it's empty and you blow it up, the radius changes very rapidly. The rate of change of our radius with volume is very rapid at the beginning, right? And then think about it, when the balloon is really big and you're still blowing it up, it's still inflating, right? Still gradually getting bigger, and the radius is getting bigger because the volume's getting bigger, but the rate at which the radius is getting bigger is smaller than the rate at which the radius is getting bigger when the volume is small. Okay, so just kind of think about what it means, like physically, you know, to intuit your way through it. We didn't show you like what the rate of change of the radius was when the volume was small. Okay, this is just when the volume is fairly large. Okay, so that's how we're thinking about it. The rate is a really important concept, right? Because the rate of change of something is going to give us an added dimension of information, okay, about what's actually happening. Okay, is all good with that example? Okay. So like I said, for the stepwise function, I'll write down the solutions for it and then I'll post it online with our lecture solutions. So I'm going to skip that one just for now for time's sake. And then you'll be able to see the solutions for that when I post them later today. So there's a couple of things, couple of ideas that I just want to wrap up this chapter section with, and then we'll move on to chapter 1.2. We're going to finish it. Okay, so I've got a couple of definitions. So the things I want to define. Okay, so the first thing I'm going to define is what we think of as position, right? So the position of an object on the line of travel, and we're going to assume it's a straight path. Is simply its coordinate on some axis that we make, right? And we're the ones, we can define what that axis is if we're observing something. But with a position, right, I've got my axis, my direction. I'm going to define this as a positive direction. My positions are positive, right? And this is, I'm going to define, arbitrarily speaking, as my origin. And then I'm going to define this as a negative direction of travel, negative position. Leading into, I'm not talking about it specifically, but I'm leading into the concept of vectors versus scalar, right? So position is going to be a vector, right? Where I start, like you can imagine, let's do this. So I start here and say I end here, okay? So this is my start position, this is my end position, okay? But I could also have it be like, I could start here and I could end here. Okay, so my ending position is going to be negative, okay? But it just means that's where we are in relation to our coordinate on the axis, okay? So for position. Now when we think about average velocity, okay? Our average velocity is the average rate of change of the position of the object with respect to time. Our average velocity is a vector, right? Because we're dealing with position. We talked about this briefly where we said it's our position, right, at time t1 minus position at time t0 all over time t1 minus time t0. So it's change in position over change in time. If you can't remember, you know, what this is, remember your units for velocity, like meters per second, okay? Meters are our position, second is our time. So it's change in position over change in time. This is a vector because it's based on position, which is also a vector. Average acceleration. Okay, average acceleration is the average rate of change of the velocity of the object with respect to time. Okay, remember your units again, meters per second, okay, is our units for acceleration, right? Meters per second squared. So it's the change in velocity over the change in time, average acceleration. This is also a vector because it's based on velocity, which is a vector. It's different than our average speed. Our average speed, right? Speed and velocity are similar, but speed is a scalar. It doesn't have direction. It's based on the average rate change, what we're going to call total distance traveled by the object with respect to time. Okay. So we did, let's see if I can get a pen. Right, so we did our position started here and ended here, but imagine if I wandered all around, it took me a while to actually get there, right? This is my total distance traveled. It's our footpath, right? Or maybe, you know, I ended up here and I went there, but my total distance traveled was like all over the place, right? So if you go on a straight line, right, your total distance traveled and your total displacement, right, from the start to the end, okay, are going to be the same, but it's possible that the total distance traveled will be greater. Total distance traveled is always positive. Okay, we're not talking about it in too much detail here, but vectors give you a whole wealth of information about things, right? They give you a direction, okay, what direction am I actually going in? And then as well as they're also giving you like a magnitude, what's the length of that particular vector, okay, whereas the scalar is just a number, okay, and it represents different things. Okay. All right, so that was the last bit that I wanted to cover for chapter 1.1. You guys can take a look up online for the lecture examples that I'll post up there in addition to the solution set for example 5 for chapter 1.1. Okay. You guys all done writing this down here? All righty. So, go ahead and get started on chapter 1.2. Okay, so chapter 1.2 is interesting. Our book calls it the prelude. It's like an introduction to the instantaneous rate of change. We'll talk about what that means. Prelude, the IROC. Okay, so there's a lot of things that we're actually going to be using today that we haven't covered in a lot of detail. It's kind of funny. Our book does this a lot, and I'm always tempted every semester I teach this class to start with chapter 1.3 and then go into 1.2, because we're going to be using the idea of a limit without actually really in detail defining it for you. So kind of bear with me. If some of these terms don't make a whole lot of sense, don't worry about it. We're going to spend a lot of time on limits and derivatives and all that, but we're starting to introduce this concept. Okay, so we're going to ease into the idea of the limit. Some of you may have heard of limits or used limits before, and some of you may not have, which is why we spend actually a lot of time on it. It's such an important concept. Okay, but first, let's talk about how we can think about it conceptually. I've got my coordinate axis, and I've got some function of x, right? So now, let's imagine, right, I've got some x value within the domain of my function. And then right here, right, so I've got an x, y pair for a particular value. So this point right here represents right along my domain. I've got this value of x, that it has a y value associated with it, right? So I've got this value of x. I'm going to move some delta distance, right? And I'm going to call that delta an h, right? So okay, x plus h, some distance away from my x. So if x is 5, this is maybe x plus 6, you know, some value, some farther away value than where I'm at right here, some delta, okay? I now have a new y coordinate, okay, for this. This is a new point, right? This is my x plus h. This is my function at that x plus h value, okay? So now what we've been doing in the previous chapter is we've been making, right, a secant line, right, the slope of which is our average rate of change, okay? So you can imagine where if I made this h a little bit smaller, so this distance away from x was a little bit smaller, right? So this is like some other value, kind of made it a little bit smaller. And then I have some other value right here. And I'm going to make another secant line. The slope of this is equal to the average rate of change between here and here, right? I went a little bit closer, okay? And then I can just keep going and going and going, making all of these different secant lines, right? I'm going to go a little bit smaller. I've got another secant line as I'm going, right? Here's another secant line, and so on and so forth. The whole point of which is because my instantaneous rate of change says what's happening at x, right? What's our rate of change of our function f of x at x, right? So I need to be able to use the average rate of change, my secant line, to help me approximate what's actually happening at x right here, my instantaneously. So I'm going to go x and then x plus h. I'm going to decrease that distance between x and x plus h. I'm going to make h smaller and smaller and smaller. I'm going to make all these secant lines until I basically get so close to x that I'm essentially sitting on top of x, okay? So let's write that down in words, okay, because that's what we're actually trying to do. Our goal is to figure out what's actually happening here. What's our rate of change at x instantaneously? But we need to kind of approach it from a distance, okay? So let me write that down. So it's going to look like this. So as h gets close to 0, so that means my delta, right, the value, this distance between x and x plus h, as that gets smaller and smaller. As x gets close to 0, x plus h gets close to x, right? That distance gets smaller and smaller. And f of x plus h gets close to f of x, right? We can see that, right? We're getting closer and closer and closer to f of x, okay? So what we're going to do is we're going to use the average rate of change, okay, that's our slope of our secant line, between x and x plus h, right? And I'm going to keep iterating this, keep calculating my average rate of change as I make this distance, as I make h smaller, as I make that distance smaller and smaller and smaller. Right? So I'm going to keep calculating the average rate of change with smaller and smaller values of h. Okay? So we say as h approaches 0. That's how we read this. As h approaches 0, I'm going to keep calculating smaller and smaller values. Okay? Except that I don't want to sit here all day and do it. So we need to have a mathematical way of representing that calculation where I make this infinite number of calculations between x and x plus h, bringing h closer and closer to 0 so that distance gets smaller and smaller and smaller. Okay, so that brings us to our preliminary definition of a limit. Okay. We're going to do a preliminary definition of a limit. I'm also going to do a preliminary definition of the instantaneous rate of change. and a preliminary definition of the derivative. We're really introducing things today, okay? But we're going to cover them in detail and in depth as we go along in the next, couple of weeks, okay? So bear with me here. So for in terms of limits, okay? So let's talk about our limit. So if I've got some function, q, and it's a function of h, okay? And this function, it's arbitrarily close to some number, some number L, okay? So we've got this function, it's a function of h, and it's going to get close to some number L as h close to 0, okay? So as h is getting smaller and smaller, this function q of h is approaching a specific number. We'll be able to start seeing it next week. We're going to actually, do this calculation out, so we'll see these numbers as we approach them, okay? So then if this is true, we say the limit of our function q of h as h approaches 0 exists. We're going to talk in detail how we know if the limit exists or not. We'll talk in detail next week. Exists and is equal to this number L. A lot of words, so we have a mathematical way of writing it. We say the limit as h approaches 0 of our function, q of h equals L. That's how we read that. Okay. It's a preliminary definition of a limit. If this is your first time seeing limits or you feel a little bit unsure about limits, don't worry. We're going to spend a full week on limits, so it'll become really clear by the end of next week. Okay. You guys finish writing that, and then we're going to talk about how we're going to use this idea of a limit to help us define the IROC and the derivative. Guess all set. All right. So now I'm going to keep going on with the definition. So this is another definition. Right? So suppose we have some function y equals f of x. Oops. Okay, and we let q of h be the average rate of change of that function, f, okay, with respect to x. You remember, our average rate of change is our slope of our secant line. Okay, so I've got this function. It's kind of like what we did before, right? I've got this function. I've got a secant line. Okay, the average rate of change, okay, is the slope of that secant line. So this function q of h is going to be the average rate of change of our function f with respect to x between the values of x equals a and x equals a plus h. It goes back to that graph that we just did, right? Where I have x and I have some distance away, x plus h, that I'm looking at. Okay. And now what I can do is I can write q of h equals, I'm going to check the slope. This is the average rate of change, is the slope of that secant line. I'm going to go a plus h minus f of a all over a plus h minus a, which I can simplify the bottom to be plus h minus f of a all over h. This here we're going to use to help us, right? This is our slope, the secant line between x equals a and x equals a plus h. Okay. What we're going to do is we're going to decrease h, right? So as h gets smaller and smaller and smaller and smaller, we're going to keep taking this slope value until it approaches some number. And we're going to use that to help us define the instantaneous rate of change. Remember, these are all preliminary definitions. We're going to really go over it in detail a lot this semester. So the instantaneous rate of change of our function f with respect to x at x equals a. Now remember, our secant line was x equals a to x equals a plus h, right? And now we're looking at what's our instantaneous rate of change, okay? Right at x equals a. I want to know that, but I can't just plug it in and say what's the rate of change at this value. I need to look at all of these secant lines as they get closer and closer and closer to this value here. That's as h gets smaller and smaller and smaller, okay? So we're going to say our instantaneous rate of change of our function with respect to x at x equals a, we're going to say that it exists. We're going to talk about existence next week. So it exists if for this particular function here, q of h, right, this slope value, our limit as h approaches 0 of q of h equals a number, right? So the IROC, our instantaneous rate of change, is equal to that limit. Okay, I'm taking the limit, so I would say my IROC is equal to the limit as h goes to 0. I'm going to write it out here. F of a plus h minus f of a all over h. Right? So I'm taking all of these slopes of the secant lines, and I'm decreasing that distance between x and h. Okay, so I've got a secant line, 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 until I finally get to the point where there's no distance between the value of x that I want and the little delta value. Okay, and then basically what we're looking at is the slope of the tangent line. We're going to talk all about that in detail. This is why it's a preliminary discussion. Okay. Lastly, we use our instantaneous rate of change to talk about the derivative. Okay, so our derivative of our function at x equals a, okay, is the instantaneous rate of change of our function with respect to x at x equals a. Okay, and we can denote it like f prime of a. If it's not completely clear, hold that thought. We're gonna talk about this in a lot of detail. This is just the prelude. Okay. Now be really careful when we're dealing with limits. I can't just simply plug in h equals 0. I got to actually work it through and then think about strategies for how I'm going to be doing this math here. Because obviously I plug in h equals 0 here, I'm going to get a divide by 0 error. So it's all going to very much depend on the function that we're working with. We're going to go through examples so you can start to see some different strategies for working through the algebra on this stuff. Yes, anybody still need to write here? Good. Okay. Okay, so my lecture examples. I'm pulling out example 1. So we've got this a widescreen TV. Remember that from the previous chapter, right? Where we had that 16:9 aspect ratio, right? We've got area as a function of diagonal length, okay, which we calculated before, right? 144 over 337 d squared. Okay, so it's a parabola, okay, that we're dealing with here. So we've got a couple of questions. What's our IROC, or instantaneous rate of change of our area with respect to d when d is equal to 40? We want to know what's our IROC when d is equal to 52, and then we want to come up with just a general formula for it for any value of d. So let's work our way through. So the first thing, I'm going to just write this down again. So a of d is 144 over 337 d squared. Okay, this thing here is a constant, right? I'm just going to call it C. C equals 144, 337. You don't have to do this. Sometimes we can just make the equations a little easier. So I can go A equals C B squared. Okay, so that means I kind of replace this, so just things look a little bit neater when I'm working through, and then I'll substitute in C equals this fraction here at the end and then multiply it out. You don't have to do this if you don't want to. All right, so the process that we're going to do is this. We're going to calculate our average rate of change of our area function between A equals 40, right? That's what we were asked to do initially, 40, and D equals 40 plus some delta H, right? 40 plus H, okay? We're going to keep on saying H is not equal to 0. We're going to, and then we're going to keep changing it. We're going to make H smaller and smaller and smaller and smaller until we actually sit right on top of super, super, super close to D equals 40, okay? We're going to keep iterating. Calculation. I'm going to keep repeating that calculation as H gets closer to 0. This is where the limit comes in, right? Because you don't want to actually do it, yourself. So we're going to be looking at A of D plus H minus A of D all over plus H minus D. This is our slope of our secant line, right? That formula. Okay. So let's think about it. When D is equal to 40, this is part A. D equals 40. So I'm going to put 40 into here. So I'm going to look at is A of 40 plus H minus A of 40 all over 40 plus H minus 40. Okay, so now what I'm going to do is I'm going to remember how we said C was a constant, and this is our function, so CD squared. So I'm going to factor out the C. I just have to remember to multiply it later when I'm actually working it through. So plugging it into the actual function, I've got C times, right, 40 plus H. I'm going to plug in 40 plus H into my D squared for that equation. I'm going to go 40 plus H squared minus 40 squared, right? So this would be C times 40 plus H squared minus C times 40 squared. I factored out the C. And that's all over 40 plus H minus 40, right? The 40s are going to cancel here. I'm showing you all the steps just so you can see where all the algebra comes from. We'll start skipping steps later. So I'm going to FOIL this out. So I've got 40 squared plus 80H plus H squared minus 40 squared. Whoops, there. All over H. So I'm going to keep cleaning it up. So this is going to be C times 80H plus H squared all over H. You can see what I'm going to do. I'm going to factor out an H here. So I'm going to get C times H, 80 plus H all over H. Okay. H's are going to cancel, right? So I'm going to get C times 80 plus H. And this unit is inches squared per inch. This is our average rate of change. Oops, sorry, you can see that average rate of change. Okay. Now, after I've done that calculation, what I want to do is I'm going to take the limit of my average rate of change. I'm going to take the limit of that. So it's going to be the limit as H goes to 0 of this function here, C, 80 plus H. So now H is in a position where I can substitute 0 in. We're going to talk all about how we solve limits later. Okay, but right now, right, what I'm going to get is this is equal to, right, as H goes to 0, this is just equal to C times 80. Okay. So now I can plug in C. So remember C equals 144 over 337. So then this is equal to approximately 34.18398. This is inches squared. Inch. That's the instantaneous rate of change, okay, when our diameter is equal to 40. Right? I couldn't just plug it in, I had to actually calculate it out. This is the whole, what we call the definition of the derivative. It's something that we're going to ask you on exams and stuff. So be very careful. If you've already had a little bit of calculus and you've had like the power rule and stuff, you'll kind of recognize what I'm trying to do here. But be very careful because we always ask on exams using the definition of the derivative, okay, which is what this is. What is the answer to this problem? If you use the power rule, you won't get any credit for it, which will be really painful. All right, so let's do part B. So part B said, okay, so what's the instantaneous rate of change when the diameter is equal to 52? Because we're going to do the same process that we just did. Now instead of 40, we're going to have 52. Okay, so I'm going to go C times 52 plus H squared minus C times 52 squared. So this is my A times D squared, all over 52 plus H minus 52. I'm going to clean that up. So C times, I'm going to FOIL things out. So it's going to be 52 squared plus 104 H. It isn't working. H squared minus 52 squared all over H. Going through the same algebra that I did before, right? And that's equal to C, 104 plus H, right? So I had 104H plus H squared all over H, factored out the H, canceled it, and I'm left with this, okay? Now I'm going to take the limit as H goes to 0. It's going to be C, 104 plus H, and that's going to be equal to C times 104. And I can plug in, remember C is equal to 144 over 337. So then our answer is equal to approximately 44.4391. This is a rate, instantaneous rate of change. The area, right, is changing. When the diagonal is equal to 52 inches, our area is changing at a rate of 44.44 inches squared. Okay. I'm going to scroll up just a little bit. Part C said, let's do this for any D. Okay. So I'm, instead of like actually plugging in a value for D, I'm just going to leave it as D plus H. Okay. So that means I'm going to say A of D prime equals, and I'm going to write the limit out at the beginning. The limit, H goes to 0, A, D plus H minus A of D all over plus H minus D. Okay, which is going to equal to, I'm going to start plugging in our function. The limit, H goes to 0 of C times D plus H squared minus C times D squared all over H, right, because the D's are going to cancel here. I do some algebra. Limit H goes to 0, C times D squared plus 2DH plus H squared minus D squared over H. You have to watch your algebra. We'll talk about some tricks for algebra later. Suppose the limit goes to 0 of C times 2 times D plus H, right? So the D squareds cancel. I factored out an H and I canceled that with the H in the denominator, and I'm left with my constant times 2 times D plus H. Okay, but now the limit as H goes to 0 is equal to 2CD. Okay, which if C is equal to 144 over 337, my derivative, my instantaneous rate of change for any particular D value is going to be equal to 288, 337D. And this is going to be inches squared per inch. Okay. So far, so good. Give you guys a second to finish writing that. And then I'm going to draw a picture using this. Our constant terms times D squared is just a parabola. So we're going to draw pictures so you can see what that looks like. You guys okay if I turn the page? Tell me if you're not. Okay. So this is the using the same. So we've got A of D, 144, 337, D squared. Okay, so let's draw that out. So it's going to look like, so here's our D, our A of D. Right, so it's a parabola. It doesn't make sense really to have a TV with a diagonal of 0. It's not a TV at all, right? But I have a parabola that goes like this as our function. Okay, so remember, so if I go, here's 20, I'm going to correspond to some area, right? So it's like I'm going to say 144, 337, 20 squared. I got to plug that into my function. 40. Right, so this is 144, 337, there's 40 squared, right? It's just to help you conceptualize what we're trying to do here. This is 144, 337, 50 squared, right? So it corresponds to these different values. So imagine, right, if I had a secant line from here to here. Okay. And then imagine if I change that distance and I had another secant line, I'd have a secant line going from here to here, right? And then I made that distance even shorter, right? And then I had a secant line going from here to here, okay? You can kind of see how, like, as I get this distance closer and closer, I'm approaching essentially, like, these are all of our secant lines, right? This is a secant line. Secant line, remember, has two. I need 2 points on my function, right? Whereas if I want to know the instantaneous rate of change, right, at this particular point, x equals 20, say, for example, I'm going to keep reducing the distance between 20 and other values, right, until I get really, really close to 20. So I'm basically just sitting right on top of 20, okay? So the secant line, the slope of our secant line is our average rate of change. Okay, that's what we've been doing before. That's our slope, right? And I'm going to keep changing that distance, bring that h down close to 0, right? So basically what we're trying to do is, let's see if I can, you guys can see this, but the yellow isn't the best one. My whole point right here is to get to what we call a tangent line, right? The tangent line is the limit of our average rates of change, right? Tangent line touches at only one particular spot, okay? So it's the limit of our average rates of change, okay? All of these secant lines, as I bring it down, I want to know what's my instantaneous rate of change right at this particular value. So I've got all these secant lines and I make all these secant lines, right? I get that distance really, really small. And then these secant lines approach my tangent line right at this particular point right here, okay? So this is like kind of graphically, right, what we're trying to do. We talk about this distance here, delta x equals h. Okay, I'm going to make this as h gets closer to 0, my secant lines approach tangent line. The slope of our tangent line is our derivative. Okay, and that's our instantaneous rate of change at x equals a, that particular value, right? We want to know tangent line hits that function at only one spot, x equals 20, say, for example, right? And so when I look at the slope of that tangent line, right, it tells me what's the rate of change of my function at x equals 20, okay? But we think about derivatives, we think about power rule, we think about all these shortcuts, right? But it comes from, okay, taking a secant line, taking that slope of that secant line, bringing that secant line, bringing that distance between where I want to look and where my delta is, bringing that distance really, really super close to 0. Okay, so I'm basically sitting right on top of where I want to look. Okay, and I want to look at that spot because there's something happening there that I want to know about. Okay. Okay. You guys good so far? Okay. All right, I'm gonna put this aside and then I'm gonna talk about a couple things and then we'll do some more examples. So just some vocabulary so that we're on the same page about stuff. So I've got, in terms of definitions, I have an instantaneous velocity. So in terms of instantaneous velocity of an object, the instantaneous rate of change of the position of the object with respect to time. So if P of t is our position function, position at time t, okay, then P prime of t, okay, is our instantaneous velocity. Sorry, I'm not spelling that very well. Velocity. Okay, so I have position. I take the derivative of position with respect to time. It's going to give me velocity. Okay, remember your units. Meters per second. Okay, meters is my unit for position, right? Second is my unit for time, meters per second. So change in position over change in time at a particular time, it's going to give me instantaneous velocity. Instantaneous acceleration. Of an object. See where this is going. Is the instantaneous rate of change of the velocity of the object with respect to time. Okay, so if our velocity is v of t, right, then that means at time t, right, then the instantaneous acceleration is equal to v prime of t. I take the derivative of my velocity to get my instantaneous acceleration at that particular time t. Talk about speed really quick. Instantaneous speed of some object, the IROC of the distance traveled by the object with respect to time. So if v of t is our function representing distance at time t, a distance traveled, sorry, traveled, then d prime of t is equal to the speed. Okay. I think I had time to do maybe part A. Part A of example 3. We can maybe start it. You guys good with this? Can I move this so I can? Okay. right, so example 3. So particles moving along our axis position p meters, time t. P of t equals 5t squared minus 40t. So part A says, what's the instantaneous velocity of the particle at any arbitrary time t in seconds? Okay. So part A, we're going to take a look at. So we're looking at the IROC of the position. Okay. So that means I'm going to say my velocity equals my derivative of position, which means I'm going to take the limit as h goes to 0 of p of t plus h minus p of t all over h. Remember, it was t plus h minus t, but I'm just going to truncate it down, just say h. Okay. Those filling in the blanks. So t plus h, I'm going to plug in for t and t. Okay. So I'm going to go the limit as h approaches 0 of 5 times t plus h squared minus 40 times t plus h minus 5t squared minus 40t. Right? This is our p of t plus h. This is our p of t. The whole thing is over h. So now there's algebra that we have to do in order to multiply this out, combine all the like terms, and then find a way to simplify so I can get h out of the denominator. Okay. And just to warn you, there's some algebra going on. Let me just go through that quickly. So it's going to be limit as h goes to 0, 5t squared plus 10th minus 5h squared minus 40t minus 40h minus 5t squared plus 40t all over h. Okay. This whole thing, after combining all the like terms and simplifying, is going to simplify down to the limit as h goes to 0, 10t plus 5h minus 40. Okay, so now I can work through this, right? I don't have an h in the denominator anymore, so I can work through this, which means that my velocity, once I evaluate the limit, is equal to 10t minus 40. And this is in meters per second. Give yourself plenty of space to work with the algebra. When we pick up on Monday, we've got, I'll finish up this example, and we have another example that has a trick with radicals so that you can think about how you're going to be solving an equation with radicals, because you need some tricks to be able to work through those. But we'll talk about that on Monday. Okay. If you guys get a chance, take a look at the homework so that we can I can answer questions on Monday about homework problems for 1.1, 1.2, and then we'll wrap up 1.2 and then we'll start on 1.3. Okay, guys. Have a great weekend.
Thank you so much.
Bye-bye. Take it easy.
Thank you.
Bye.